Welcome everyone. I'm Vito Ilacqua. I'm a scientist in the Indoor Environment Divisions at the Office of Radiation and Indoor Air at EPA. And in this webinar today, we continue to focus on indoor air cleaners as we did in our August webinar, which discussed health implications. But as you may have seen in the press lately, there is much interest in understanding the regulatory context for the development, the testing, and the marketing of air cleaners, in addition, of course, to the results of research on effectiveness and safety. So today, then, we will start off addressing the regulatory framework before moving on to some of EPA's own research results. And both of our speakers today are from EPA. Our first speaker will be Aline Heffernan. She's currently the regulatory advisor in the antimicrobials divisions, where she's been for 7 years. She has worked as the review coordinator for SARS-CoV-2 during the pandemic, and she currently chairs the device and FIFRA jurisdiction work group. She has both her undergraduate degree and her master's in public health from the State University Systems of New York. And after her presentation, Dr. Catherine Ratliff is a physical scientist and principal investigator in the Homeland Security Research Program in our Office of Research and Development, where she uses models, lab studies, and field-scale studies to develop strategies for remediating environmental contaminants of all kinds. But she is also leading the EPA's research efforts to evaluate the efficacy of various air treatment technologies against airborne pathogens. And Dr. Ratliff received her BA from Vanderbilt University and a PhD in Earth and Ocean Sciences from Duke University. After our two speakers' presentations, then we will have time for questions. And please enter your questions throughout the presentations. We may have to combine them to ask to our speakers, given the size of our audience. And lastly, just two reminders. Because today's content is a mix of regulatory and research topics, I'll leave it to our speakers to indicate when their views are their own and when they represent the views or policy of the agency. And a reminder for everyone is that the webinar is being recorded and will be available as a video between 2 and 4 weeks or so after today. You can find the video of this one and of previous webinars by searching indoor air quality on the EPA site and then following the links to our webinar series. And with that, Aline, the spotlight is yours.
Okay, so hello everybody, and thank you for the introduction, Vito. I'm Aline Heffernan from the Office of Pesticide Programs, and I'm the chair of the Device and FIFRA Jurisdiction Work Group. Today, we're going to go over quickly what FIFRA is, what a pesticide is, what a pesticide device is, and how that is different than a pesticide and specific air treatment pesticides and devices. The Federal Insecticide, Fungicide, and Rodenticide Act, or FIFRA, is the act that regulates pesticides and pesticidal devices, like some air purifiers. A pesticide is a product that kills, repels, or mitigates a pest, including microorganisms. The act is specifically around pesticides that are sold or distributed. Here are two examples. The product on the left is a registered pesticide, and the product on the right is a device. The product on the left is defined as a pesticide that's a substance or mixture of substances intended for preventing, destroying, repelling, or mitigating a pest. It has a pre-market review, including data that's been reviewed by the agency and a label that's been approved before the product is sold or distributed. The product on the right is a device, and FIFRA defines a device as any instrument or contrivance other than a firearm that is intended for trapping, destroying, repelling, or mitigating any pest or form of plant or animal life. This does not include equipment sold for the application of pesticides. It has very few label and data requirements, and there is no pre-market review for these products. The label and the data are not reviewed by the agency before the product can be sold or distributed. This slide shows some common antimicrobial devices, such as UV lights, ozone generators, and hypochlorous acid generators. Most of these products are used to treat surfaces, but products like these can be used as air treatment devices. Devices are not registered like liquid disinfectants are. Devices were clarified in the 1976 Federal Register Notice. This Federal Register Notice explained that a device is an instrument or contrivance that works by physical means, such as electricity, light, or mechanics, and that a device cannot contain a substance or mixture of substances intended to prevent, repel, destroy, or mitigate any pest. Some examples from the Federal Register Notice include fly traps, fly ribbons, sound generators, carbide cannons, and UV lights. This clarification worked really well in 1976, but not so well today. Devices are required to be made and labeled in an EPA establishment, and that number must be on the packaging, and the product cannot have any false or misleading claims. As a note, Health Canada's Pest Management and Regulatory Agency, or PMRA, has started registering UV lights and ozone generators. Please reach out to Health Canada if you intend to sell or distribute your product in that country. Here you can see the difference between devices and registered pesticides. Essentially, a liquid pesticide and a device can have the same disinfection claim, but only a liquid device has data that's been reviewed by the agency and has a label that has been reviewed and stamped before the product can enter the channels of trade. A device does not have an approved label or reviewed data before the product can enter the channels of trade. Pesticides and devices are required to be produced in an EPA registered establishment and must meet annual production requirements, which can be seen here in the fourth row of the table. Pesticides have an EPA registration number and an establishment number, while potentially compliant devices only have an EPA establishment number. As you can see here, the labeling requirements for devices are limited to no false or misleading claims, but both are required to have production requirements. Common antimicrobial devices include UV lights, air and water purifiers, generators, including hypochlorous acid generators, chlorine gas, ozone that's used in both air and water, and photocatalytic apparatus. Pesticidal claims include mitigating pests such as microorganisms, allergens, which includes pests such as mold, mildew, and dust mites, and organic contaminants, which also includes microorganisms. Products called purifiers, or those making similar claims to purify, are likely regulated by FIFRA. As a note, not all air purifiers are pesticides. Generally, purifiers that are regulated in some way by the agency tend to have multiple claims, but that's not always the case. Certification claims referencing non-governmental organizations, such as the National Sanitation Foundation, or NSF, may be pesticidal claims if their standard includes mitigation of a microorganism. So, for example, a water filter with an NSF standard 53 is considered a pesticidal claim because NSF standard 53 includes cryptosporidium. Products also cannot make disease prevention claims. So, for example, a pesticide cannot say prevents COVID-19 or prevents the disease of COVID-19. However, a pesticide device can make claims for microorganisms, such as the product kills SARS-CoV-2. Sorry about that. Non-FIFRA regulated products are generally considered cleaners or degreasers. For devices, air and water cleaners that make no pesticidal claims are exempt from FIFRA and are regulated by the U.S. Consumer Product Safety Commission. And generally, these products are considered cleaners or deodorizers. If the product is an air cleaner and it does not make any claims of preventing, killing, or mitigating a pest, the product may not be regulated under FIFRA. More information on if a product is considered a cleaner can be found at the link in green. One of the labeling requirements for devices is devices cannot make false or misleading claims. Common concerns with potentially false or misleading claims include germs or germicidal. Germs has an EPA definition, and unqualified germ claims, it's assumed that the product kills bacteria, viruses, and fungi. If this claim is qualified, it should lead to the types of microorganisms that are killed. A qualified germ claim may lead to specific species of bacteria and viruses. The allergen claims include living organisms that are considered pests, like mold or mildew. This claim can also be qualified to remove all living organisms. So the allergen claim would only be for things like pests, pet dander, and dust. The claim disinfection or disinfectant have specific efficacy standards that are defined by the EPA. If a device makes this claim, the company is expected to have data on file that proves the product can kill the appropriate amount of microorganism. Purify can be a pesticidal claim depending on how it's used and how the product is sold or distributed. Sterilization and elimination are considered complete microorganism eradication claims, and these must meet EPA standards for sterilization. Safe is considered the quintessential false and misleading claim. Generally, pesticide products cannot have the term safe or be marketed as safe, as it's considered false or misleading. And finally, chemical-free is also considered false and misleading and a comparative safety claim to register pesticides. This is not a definitive list of false and misleading claims. These are just some of the ones that we see most frequently. Although there is no pre-market review for devices, EPA generally applies the same efficacy standards to pesticide devices as registered pesticide products. A minimum public health standard for antimicrobial products is 99.9 inactivation, or meeting our sanitation standard. Performance below this level would not meet EPA's public health standard. If a product cannot make sanitization claims, they cannot make specific public health claims. To support a sterilization claim, all microorganisms and test spores of the listed organisms should be inactivated. Generally, if a claim is not allowed on a registered pesticide, it would not be allowed on a pesticidal device. All devices should have data on file to support the claims and show that they are not false or misleading. Any product used against a public health pest should have specific testing on that organism to substantiate the claims. Standards for pesticides are used as a reference regarding device efficacy standards, or studies rather. Claims for sterilization without label claims for the appropriate microorganisms may be considered false or misleading. Disinfection and sanitization are EPA terms of art with specific kill rates. If the EPA label contradicts, if the device label contradicts EPA standards, the product may be considered false or misleading. As I've said before, there's no pre-market review for pesticide devices. Therefore, EPA does not review product labels, including directions for use, before it reaches the marketplace. Directions for use are a required part of a device label. Directions for use should be clear and concise and allow the user to operate the device and target the specific pests. Common problems include efficacy testing for air purifiers that's conducted in the room the size of a closet. However, the directions for use indicate that the product may be used in a large room, such as an auditorium. There are a number of other common issues that are seen when OPP or the Office of Pesticide Programs sees data associated with air purifiers. Although EPA does not review the data, we recommend data be on file and the testing should match the directions for use for the product. Air treatment devices are instruments or contrivance that work to physically trap, repel, mitigate, or kill a living organism in the air. If the air treatment product does not make pesticidal claims like kills airborne bacteria, the product may not be a pesticide. The claim air purifier may be considered a pesticidal claim depending how the product is used and marketed. For questions regarding if the product you are selling or distributing is a pesticide or a pesticide device, please submit a PREA application under code M009. An M009 is a Pesticide Registration Improvement Act, or PREA submission. This is the agency's fee for service for review of for FIFRA determinations. An M009 has a 6-month time frame, and during that time, EPA will review your product and make an official determination if and how it's regulated under FIFRA. Any company with a U.S. address may request a FIFRA determination. EPA cannot make a FIFRA determination over email or phone call. The following are FIFRA exemptions that are included in the PREA M009 category. The PREA M009 category can determine if a product is a device, an exempt treated article, an active ingredient, a barrier, a cleaner, or a minimum risk pesticide. You can also request a determination to see if your product is a pesticide requiring registration. Our determinations are brought to the Device and FIFRA Jurisdiction Work Group. This work group includes all of our registering divisions in the Office of Pesticide Programs, our Office of Enforcement and Compliance Assurance, our Office of General Counsel, and several EPA regions. We discuss the product and may respond with some specific questions. If you are unsure if your product could be regulated under FIFRA and want specific instructions on how to submit an M009, please email me at the device mailbox. It is in green on the slide. So it's OPP_FIFRA_jurisdictional_issues@EPA.gov. There is not a one-size-fits-all for a pesticide determination for air filters. For an air filter to be considered a pesticide under FIFRA, claims against microorganisms must be made. If an air filter does not make any claims against a living organism, it is not likely a pesticide. Recently, EPA has seen a number of air filters that have been treated, and a treated filter may be considered a device or a pesticide requiring registration depending how the treated filter works. So, for example, a filter treated with silver. Silver is a substance with known antimicrobial properties and is a known antimicrobial active ingredient. If this silver is not registered, this product may be considered a pesticide requiring registration, as the filter would work chemically and contains a substance. However, if the filter works via physical forces, via van der Waals forces or electrostatic charge, the product may not be considered a device, as the antimicrobial activity is mechanical. I would also like to discuss a few other examples. Generally, when a chemical substance is added and adds a pesticidal effect to the product, it may be considered a pesticide requiring registration. A liquid chemical, such as a quaternary ammonia product or a quat product, makes air purifier claims or air disinfection claims, it would likely be considered a pesticide requiring registration. Here, there are pesticidal claims and there is a substance, the quaternary ammonia. Because the product is sold with a substance, i.e. the liquid chemical, it would be considered a pesticide requiring registration. If there is an air filter that's making air purifier claims, and it is simply an untreated HEPA filter, this would likely be a device and not a product requiring registration. If there's an air filter and an air purifier that has been treated with some type of substance and is making direct pesticidal claims, this is where it gets tricky. The product could be a pesticide requiring registration, or it could be a device, depending on the substance the filter is treated with, how that substance works, and if that substance has been registered for use as a materials preservative. As you can see, there are a lot of likelies and mays in the examples. So if you have a question, if your product is a pesticidal device or a pesticide requiring registration, please submit a PREA application code under M009. If you have any questions whether a pesticide is regulated under FIFRA or have any claims if your label is false or misleading, please email questions to opp_FIFRA_jurisdictional_issues@epa.gov. Some emails may direct you to submit an M009 and information will be provided. And please note your email may be redirected to another different part of OPP for an answer. Okay. At this time, I would like to pass the presentation to Dr. Catlin Ratliff from EPA's Office of Research and Development.
All right, thanks so much, Aileen. Just want to check and make sure that you all can hear me okay.
We can hear you.
Great, thanks so much. So yes, my name is Catherine Ratliff, and I am speaking to you from EPA's Office of Research and Development. And I'm excited to follow up Aileen's great presentation, providing an overview of the regulatory issues regarding air treatment devices and talk a little bit about the research that EPA has been conducting over the past few years with these types of devices. So as Aileen alluded to, there are many different types of air cleaning and treatment technologies. Many of these technologies work to inactivate infectious aerosols, and I'm typically going to be referring to those technologies that kill or inactivate microbes in the air as air treatment technologies, but there's other kinds of technologies like those that mechanically filter or otherwise reduce concentrations of infectious aerosols through mechanical means. I typically will be referring to those as air cleaning technologies, but I'll be using this terminology interchangeably throughout the presentation. So even within a specific category of air treatment devices, say, for example, those that emit ultraviolet C or UVC radiation, there can be many different types of technology. So for example, for UVC, there's the traditional 254 nanometer UV emitting devices, but there's also emerging light emitting diode devices, as well as far UV or shorter wavelength 222 nanometer UV devices. And there's also all different kinds of electronic air cleaning devices. So I'm talking about things like ionizers, photocatalytic devices, and different devices that generate ozone as well. And then, as Aileen alluded to, there's also all different types of filtration technologies. So the typical in-duct HVAC filtration are a great example of these, but there's also portable HEPA cleaners and things like the specialized treated media that Aileen alluded to previously. And then there's also many different types of devices on the market that represent combinations of many of the above things. So things that include both ionization in a filter or UVC in a filter. And so, like I said, there's just many, many different kinds of these technologies. And so I'd also like to direct you to some of the EPA resources on these air cleaning technologies. There's some great resources on the web pages that exist. And so within the Office of Research and Development, we conduct research, but we also provide a lot of scientifically based technical support. And questions that we begin to get as there began to be a growing concern about the airborne transmission of COVID-19 surrounded lots of questions regarding what types of air cleaning and treatment technologies could be used by our stakeholders in different kinds of spaces. So what would be most effective, say, in a subway car or in a classroom or in somebody's office building or even in a home? And we realized as we started to look at the available data on all of these types of technologies that it can be difficult to understand truly how effective these air cleaning and treatment technologies are against infectious aerosols. And it was, again, challenging to figure out how do we compare results across studies that were conducted by different manufacturers and with different technology types. And then even more challenging can be understanding how to extrapolate results that were produced in a lab to inform predicted performance in the real world. So as I've alluded to, there's lots of different challenges that are associated with addressing the predicted performance of these technologies. And as we're talking about today, many of these things are pesticide devices, which, as Aileen covered, are regulated by EPA but not registered, and so therefore their performance is not routinely verified by EPA. And there has been some progress along these lines, but there's still a lack of standardized test methods for evaluating the performance and safety of these different technologies against airborne pathogens. So it becomes really difficult to compare results across different laboratory tests that were done by different labs and also with different technology types. If the tests are done differently, it becomes really challenging to compare those results. And another challenge is that the testing is often commissioned by the manufacturers of the devices. So it's logical to think that these tests are often done in a way to make the devices look like they perform well. So within ORD, we have been focused over the past few years on conducting testing with these different air treatment and cleaning devices under conditions that are translatable to real world settings. So we want the conditions of our testing to be representative of how these devices are used in the real world to be able to more effectively translate those results from the lab to the field. We also want to help develop those standardized test methods so that we are more readily able to compare results across studies and technology types. And again, we want to get a better understanding of what those critical elements are of the lab tests that need to be there in order to be able to translate results to the real world and really inform the predicted performance of these technologies in that applied setting. So if you take home nothing else from today, or from my portion of today, I want you to take home that the technology performance, how well these technologies perform against infectious aerosols, is truly and wholly a function of the testing environment and the test methods. So Aileen again alluded to this, but just to drive this home, imagine putting an air cleaner in a glove box, say a 1 cubic meter chamber, and running tests with an aerosolized pathogen or surrogate pathogen, and then trying to take the results from that lab test and extrapolate it to say something the size of a classroom. Obviously, there are differences between a glove box and classroom that extend beyond just the spatial extent of the setting. And then again, taking it to another level, think about trying to extrapolate the performance from the glove box to an auditorium. So what I'm really trying to drive home here is that the scale at which the testing is conducted matters. Say a 99.9% reduction in infectious aerosol in a glove box is likely not going to translate when you are looking at moving that device into a bigger setting. So taking a full a full assessment of the conditions under which the testing was performed is really important for being able to extrapolate performance to the real world. So we have been conducting within the Office of Research and Development testing over the past few years, and our specialized aerosol test facility in our Research Triangle Park, North Carolina lab. I've been using a 3,000 cubic foot bioaerosol test chamber that we're able to control temperature and humidity in. We also have mixing fans in order to ensure that the chamber is well mixed. And what's really great about this unique chamber is that it's actually part of a larger recirculating aerosol wind tunnel. So we're able to open up the chamber and quickly reduce the concentration of infectious aerosol in the chamber to nothing, based on the fact that we're able to filter the air through HEPA filters throughout the wind tunnel. And we worked closely with colleagues in the Office of Pesticide Programs and Office of Air and Radiation, as well as stakeholders in industry, to develop a mock HVAC system that is broadly representative of a range of indoor environments. We use a negative air machine to simulate an HVAC return. We don't have a filter installed for any of the tests that I'm going to be talking about today, but have installed filters for other types of testing. And within the chamber, we're running a fully recirculated air, but at about 350 CFM for this blower, so about 7 air changes per hour. And air travels from that return up to 6 different supplies into the test chamber, and we have galvanized steel duct materials as part of the HVAC system. And we have been focused primarily on using the non-pathogenic virus, the bacteriophage MS2, for the bulk of our air treatment and cleaning technology testing. this is an attractive microorganism to use for this kind of testing because it is a non-envelope small virus. And so based on the Spalding hierarchy of microbial resistance, it's expected to be more resistant to chemical inactivation and other types of disinfection technologies than enveloped viruses such as SARS-CoV-2. It's also a relatively safe microorganism to work with, or it is a safe microorganism to work with. It can be handled under BSL-1 conditions. And this is important from a safety standpoint, but it also helps to keep costs down in testing. And it's important when we're working with aerosolized microorganisms at these large spatial scales to do it in a safe way. So we aerosolize MS2 in the chest chamber using 6-jet collicid nebulizers. And the way we've been running the testing that I'll be talking about today is that we aerosolize at the beginning of the test period, and then we either turn the technology on for the technology tests or we don't turn the technology on for the control tests, and we're not injecting microorganism throughout the test period. So it's essentially one big slug of microorganism at the beginning of the test, and then looking at the decay rates with and without the technologies on after that. And I'll be focusing today on talking about results that were generated using both deionized water and simulated saliva as the aerosolization media for aerosolizing the MS2 into the chest chamber. And we sample the air from the breathing zone in the test chamber over time during the test period using SKC biosamplers, which are impingers, and also in some instances, a microorifice uniform deposit impactor or a MUDI. And we take these samples to our on-site microbiology lab and enumerate them following testing via a plaque assay. And we also take particle size and concentration measurements. We have a couple different instruments for that. A scanning mobility particle sizer, which allows us to measure the smaller size fractions of our aerosol particles, as well as an aerodynamic particle sizer, which measures the larger size fraction of our aerosol particles. And I'll be talking about this a little bit more, but we do conduct at least a minimum of 3 replicates for all of our test conditions. So how do we calculate efficacy of these various air cleaning and treatment technologies? Well, one way to do it, and is sort of the more traditional way to do this when thinking about pesticide efficacy or pesticidal device efficacy, is by talking about that log reduction. And when I talk about log reduction, I'm talking about comparing the log recovery of the positive control samples. So that means that the tests that are conducted where there's no technology operating in the test, comparing the difference between the recovery, microorganism recoveries for those positive control tests and the amount of microorganism recovered during the test with the technology on. And we believe that these time-matched control conditions are critical for calculating that log reduction, because that positive control or natural decay test condition allows you to account for the background amount of microorganism decay that isn't attributed to the technology. So by calculating a log reduction based on the difference between these two types of tests, we're able to isolate the reduction in infectious aerosol that can actually be attributed to the technology, not necessarily the amount of background decay that would be occurring without any technology operating. And another way to calculate efficacy or effectiveness, which is really attractive, is to calculate the clean air delivery rate. So a clean air delivery rate is great because it allows you to extrapolate the findings of a lab test or a chamber test to different size spaces. So it takes the volume of the test chamber and multiplies that by the first order decay rates of the microorganism or whatever the target pollutant is for the technology on and off conditions. And so when I talk about clean air delivery rates, these are pollutant specific. They're calculated for a specific target, and we'll be talking a little bit more about the nuances of that later in the results. But when I'm talking about clean air delivery rates, it's going to, again, be specific to our results in this presentation, but I do want to mention that the AHAM AC5 test for air, AC1 test for air cleaners reports a clean air delivery rate for smoke, dust, and pollen. That's the test that's used to rate most of the household air cleaning devices, whereas the AC5 test reports a microorganism clean air delivery rate, or an MCATR. But for the purposes of the results that I'm going to be talking about today, I'll be talking about a few different clean air delivery rates. And then an infectious aerosol or MS2 clean air delivery rate, that'll be denoted by a subscript of M, a smaller aerosol particle size clean air delivery rate that's measured by our scanning mobility particle sizer, or the SCATER subscript S, and then a slightly larger, the 0.5 to 1 micron aerosol particle clean air delivery rate that'll be denoted by a subscript A. And so for the purposes of the rest of today's presentation, I'm going to be talking about and demonstrating how these calculated efficacies are a function of the test methods that are used to generate them. So the first device, air treatment device that I'm going to be talking about is a far UV or a portable 222 nanometer krypton chloride UV source. So this is a commercially available far UV source with an output center irradiance of 14 microwatts per centimeter squared at 1 meter. It is an exciting technology that has been getting a lot of attention lately because the shorter 222 nanometer wavelength is less harmful to human eyes and skin than the traditional 254 nanometer UV wavelength that's used in the by the traditional low pressure mercury lamps. So as a result of this shorter wavelength, it's been proposed for use in occupied spaces. So we, for the purposes of our testing, had 2 units in the test chamber. Each of the units are reported by the manufacturer to treat 1,500 square feet of floor area, but we used 2 based on consulting with the manufacturer and their recommendations for our particular test chamber. And we conducted testing with both deionized water and simulated saliva as the aerosolization media. So now in this plot on the right, the sample time, so the test period, is denoted on the x-axis, and the amount of infectious aerosol present is represented on the y-axis. And each individual line here represented on the graph represents a single test that we ran. So again, you'll note that I stated we conduct a minimum of 3 replicates for each test. So these gray lines represent the control test where there was no far UV activated or turned on, whereas the orange lines represent the tests that were conducted with the far UV on. And the first thing I want to point out here is that even with no UV active in the test chamber, there was, for some tests, up to a 2 log or 99% reduction in MS2 over the test period. So that's the difference between the final and the starting time equals 0 concentration throughout the control test. So reporting an effectiveness or log reduction based off of comparing the end result to say the time equals 0 test result is truly misleading because you're not taking into account that background amount of attenuation and decay at this, under these conditions, that's up to 99%. That would be overstating the effectiveness of the technology. The other key point that I want to drive home here is that we believe replicate testing is truly important for characterizing efficacy. So you'll see that within a particular sampling time point, there can be a greater than a 1 log variability and the MS2 recoveries between replicates of a given test condition. So now the plot on the right, the top plot is showing the average of each of the 2 different types of test conditions, the control and the far UV. And the bottom plot is showing the effectiveness or efficacy, the calculated log 10 reduction, which is again just the difference between the 2 tests over the test time period. So at 90 minutes, we saw up to an 83% reduction in the amount of infectious aerosol present in the far UV test compared to the control condition. And there were statistically significant differences at both 60 and 90 minutes between the far UV test and the control conditions. And I should note that this is for the data that are generated using deionized water as the aerosolization media. And the story changes a bit when we look at the results that were generated using simulated saliva as the aerosolization media. So here I want to note that there's a much higher concentration in infectious aerosol throughout the test period from the control tests with the simulated saliva as the aerosolization media. So this black line represents the control tests with the simulated saliva as the aerosolization media, and this gray line is again that DI water control condition. So you'll see that there's much more microorganism present at the end of the test with the simulated saliva versus the deionized water. So the MS2 is stable, it's happier in the simulated saliva compared to the DI water. And so what's interesting is that there's actually more overall inactivation of the microorganism in the DI water test, so this orange line, compared to the purple line, are the two different far UV test conditions, with the orange being the DI and the purple being the simulated saliva test condition. Again, more inactivation for the deionized water condition. But again, we're calculating efficacy based on the difference between the control and the test conditions. So between these two lines would be the orange bars here for the DI, versus the difference between these two, the purple and the black line, is the calculated log reduction for the simulated saliva test condition. So even though there's more overall inactivation for the DI water test, the actual calculated efficacy is greater, or 96% at 90 minutes for the simulated saliva test condition. And again, we see statistically significant differences for both test conditions at 60 and 90 minutes. So now I'm going to switch gears a little bit and talk about a technology or a device that would capture and remove infectious aerosol from the airstream instead of actually inactivating it. So for the purposes of these results, I'm going to be talking about tests that were conducted with portable HEPA air cleaners. So these are two commercially available air cleaners that we used. We used 2 units in the test because they are each reported to have a smoke cleaner delivery rate of 99 CFM. So based on AHAM and EPA recommendations, they are sized to treat about 150 square feet of room area. So 2 of them fit our 300 square foot test chamber footprint nicely. We did place them in a way to minimize any sort of interference of the airflow with sampling, and again ran tests with both deionized water and simulated saliva as the aerosolization media. So these plots on the right show the results come with the DI water test. So at 90 minutes, again, this plot is showing the average of the tests conducted with the HEPA unit and the average of the controls, where the difference leads to the log reduction that's plotted in the bar chart on the bottom. And that average the log reduction at 90 minutes is 90% for the DI water test conditions, with statistically significant differences at 30, 60, and 90 minutes. And then when we look at the simulated saliva results, the story is similar to the far UV test. So again, there's more overall reduction in the amount of infectious microbe present in the air, this green line, for the deionized water test. But if we're looking at the differences between the control and the test conditions for the DI test compared to the simulated saliva test, which would be the black line and the blue line, and the log reductions, then there's actually greater log reductions that are calculated over the simulated saliva test conditions. So up to about a 99% log reduction at 90 minutes with the simulated saliva tests. And again, for these tests, we see statistically significant differences between the test and control conditions at 30, 60, and 90 minutes. So now this bar chart on the right just summarizes the calculated log reduction values for the 2 different technologies and the 2 different test conditions. And want to hit home yet again that there's more overall reduction in a given test comparing the final concentration of infectious aerosol to the initial amount of infectious aerosol for the DI water test. So that's like the 90-minute aerosol concentration compared to the 0-minute is greater for the DI test condition compared to the simulated saliva. But that story is flipped when we look at the calculated time-matched controls, which we use to calculate log reduction. So again, for the simulated saliva test, we see more calculated efficacy for the simulated saliva condition compared to the DI water condition. So what does this look like when we are thinking about clean air delivery rates? So again, the clean air delivery rates are great because they allow us to look at efficacy or effectiveness in a way that facilitates translating the results to different size spaces. So the points on all of these graphs are the bioaerosol concentrations over the test period, so the same data that you were showing, or we were shown before, and the lines represent a linear regression through the test data. And the clean air delivery rate is again calculated as the difference between the slopes of the lines multiplied by the volume of the chamber. So looking at the difference between the orange line for far UV and the control, calculated by the volume, we get a clean air delivery rate of 62 CFM for far UV, and the difference between the green and the gray is about 103 CFM for the HEPA tests. And then when we look at simulated saliva, again, the story is the same. This gray line, which represents the control data, shows much more stability in the infectious aerosol. And so Therefore, the difference between the blue and the gray and the purple and the gray is much greater than for the DI water condition, even though the slopes of these lines on the simulated saliva test condition are gentler, actually. So the decay is lower or slower for the simulated saliva test condition compared to the DI test condition for both technologies. So because of this increased stability of the control test, we get a higher calculated clean air delivery rate for far UV of 116 CFM and a clean air delivery rate of 193 CFM for the HEPA units. And I want to remind you too that these calculated clean air delivery rates are the combined effective 2 of each of these devices in the test chamber. So, you know, we again see that increased bioaerosol stability in the control condition with some stimulated saliva really, we think, is driving these differences in the decay rates and calculated clean air delivery rates. But this obviously begs the question of, you know, are there differences in the physical aerosol mechanics between the aerosol particles that are generated using deionized water and simulated saliva? You know, is there something else going on from a physical standpoint that would be impacting efficacy based on these differences and the different aerosolization media? So remember that we are also taking measurements of the aerosol particle size and concentration in all of our tests. So these plots show the mass weighted particle size distribution of the generated aerosol particles that are generated by the Collison nebulizers for both the DI tests and the simulated saliva tests. And we see that for both, the mass median diameter is actually the same, about 0.86 microns. So aerosolizing in simulated saliva compared to DI water isn't exactly changing the mass median diameter of our particle size by anything significant. But this doesn't tell the whole story. We also want to know, where is the actual infectious aerosol within this particle size distribution? So we can hone in on that by looking at results from the Moody data, the microorifice uniform deposit impactor. So again, this is a multi-stage impactor that collects aerosol particles at different size fractions. So we can take the samples that are collected by the Moody, again, back to our microbiology lab and enumerate them to figure out where the infectious microbe is in those different size cuts. So this graph on the left is showing the relative percentage of where that infectious MS2 is under different test conditions using deionized water, the dashed line, and simulated saliva as a solid line at 2 different relative humidities. And we see that for the infectious aerosol generated under deionized water, there's a peak. The majority of the infectious aerosol is in the 0.3 or about the 0.3 micron size range, whereas for the aerosol generated using simulated saliva, that actually shifts a little bit. There's a broader distribution of where the infectious aerosol is present from about 0.3 to 1 micron. So what this means is that we need to look at both of our particle size instrumentation collected samples to be able to address potential differences in the aerosol particle dynamics for these different test conditions. So the aerosol particle size may not be changing, but the distribution of where that infectious aerosol is present is impacted by differences in the aerosolization media. So knowing that, we can start to compare concentrations of the aerosol that's generated and look at how that's measured by the 2 different types of particle sizing instrumentation. So these graphs now show over a given test period the particle concentration for the different test conditions. So graph on the left is again the test using deionized water as the aerosolization media versus simulated saliva, and the particles concentration on both of these is on the y-axis here. So I'll note that the control tests are denoted in gray, or the concentration of particles in the control tests are denoted in gray, but it's actually really hard to see them because they're almost perfectly overlapped by the UV test condition for both of these aerosolization media. So essentially what we're seeing is that there's no difference in the particle concentration in terms of what the concentration of the far UV test looks like compared to the control, or no technology on tests. But with the HEPA filtration, we see that there's a decay for both DI and simulated saliva test conditions in that particle concentration. This is very logical. We would expect to see this. We know that far UV is not removing particles from the airstream. It's inactivating infectious microbe, whereas HEPA filtration is removing it. So we would expect to see these differences. But what's interesting is that for both test conditions, the amount of reduction is the same. So we see about a 96% reduction. And for this, the SMPS measured particles, less than 0.6 micron, that 96% reduction for both test conditions over the test period. And again, no reduction from the far UV standpoint, which is what we would expect to see. So there's no evidence of additional trapping by the HEPA portable HEPA units with the simulated saliva tests. And then we can also look at the slightly larger size fraction from between about 0.5 to 1 micron particles. Again, the same story holds true. There's no reduction in the amount of, or the particle concentrations are the same for the control and the far UV tests. But when we look at the HEPA units, they are reducing the particle concentrations, and it's up to about 98% over the 90-minute test period. Again, very, very logical, but interesting to see that there's not any difference between the DI and the simulated saliva test condition in terms of that particle reduction. And we can again calculate the clean air delivery rates based on the particle sizes. So as expected, similar to MS2, we can calculate across the different across the different test conditions and size ranges for the two different particle sizes. And again, as expected, there's essentially no clean air delivery rate from far UV from a particle standpoint because far UV isn't removing the particles. So the calculated clean air delivery rates for the far UV test conditions is essentially 0. But when we look at the two different size fractions from the slightly larger, the slightly smaller size fraction up to about 0.6 microns measured by the SMPS, we see the calculated clean air delivery rate for both the DI and the simulated saliva aerosolization media test conditions is about 135 CFM for this SMPS size range. And then for the slightly larger size range of 0.5 to 1 micron, the calculated clean air delivery rate for the HEPA units is about 14% larger, 20 CFM larger than the SMPS size range. And I'll note that this is actually what we would expect to see, the differences between these two calculated clean air delivery rates across the two different particle size ranges, because the SMPS bin contains the most penetrating particle size for filtration, so about 0.3 microns. This 0.3 micron size is the aerosol particle size that can most easily pass through a filter. So it follows that the calculated clean air delivery rates for this SMPS size range would be smaller than this APS size range. So, take home point here is that changing the aerosolization media doesn't seem to have an impact on the non-biological particle dynamics. Okay, so now this chart is just summarizing the various clean air delivery rates that are calculated from the results that I showed previously, where we see that the non-biological clean air delivery rates are essentially the same across the DI water and the simulated saliva test condition. But for the infectious aerosol or the MS2 clean air delivery rates, we see that aerosolizing in simulated saliva has almost a 2-fold increase in that calculated clean air delivery rate. And again, these are reported in CFM for 2 units in the test chamber. So why do we care about this? Well, I would propose this is really important to consider for selecting and optimizing the use of various air treatment and cleaning technologies in different settings. And it's even more important now in light of new guidance and standards that have been rolling out over the past few months. So for example, the CDC's new target ventilation rate is 5 air changes per hour. And CDC's guidance states that you can achieve this target through a combination of air cleaning devices, in addition to other ways to improve ventilation. And so if we are thinking about calculating the air cleaning or treatment technology and their contribution to that equivalent air cleaning, equivalent ACH, that equivalent ACH is certainly, as we've seen today, a function of the test methods that are used to generate that ACH. So the way that you test and generate that equivalent ACH is going to impact how you are getting to that target of 5 ACH that CDC has proposed. Similarly, under the newly approved ASHRAE Standard 241, control of infectious aerosols, this standard specifies an equivalent clean airflow rate that's delivered to the breathing zone in different occupied spaces with the goal of reducing the risk of disease transmission. And air cleaning is one way under that standard that you can contribute to that clean airflow delivery. And this standard is definitely a significant step forward in outlining the effectiveness and safety testing requirements for different air cleaning and treatment technologies, which again includes pesticide devices. But some of the details, including the aerosolization media, are not addressed in the standard. And we've seen based on the results that I've shown today that just changing the aerosolization media can have a significant impact on the calculated clean air delivery rate by a given technology. So, the take-home point here is that something as simple as changing the aerosolization media can have a really significant impact on the calculated clean air delivery rates that you use to get to figure out the number of air cleaning devices or treatment devices that you are using in a space to meet those CDC or ASHRAE 241 targets. So in summary, the results that I showed today show that just something as simple as changing the aerosolization media and air treatment or cleaning technology efficacy testing can have a really significant impact on the calculated performance against infectious aerosols. So again, about a twofold difference in the calculated log reduction and clean air delivery rate for both technologies. We saw that there was more overall reduction for both of the technologies tested using the deionized water test condition, but there's a greater calculated efficacy in the test using the stimulated saliva, and that's really driven by the increased stability of the microorganism in the control test under the simulated saliva condition. Also, we saw that there was not a notable impact on the non-biological particle dynamics or calculated clean air delivery rates with changing the aerosolization media. So again, those differences in calculated clean air delivery rates for infectious aerosols truly come from that increased stability that the simulated saliva provides to the microorganism. I also demonstrated that those time match control tests as well as replicate tests are really critical for characterizing and calculating the effectiveness of air treatment and cleaning technologies against infectious aerosols. And something I didn't point out while I was walking through the data, but I would like to point out here is that there is a lot more variability in the bioaerosol data than there was in the particle data. The particle data pretty much overlaid it perfectly over the replicates for each test condition, but there's certainly much more scatter in the bioaerosol data. And that's just the variability that's inherent in working with microorganisms and really drives home the point that in all microbiological testing, replicate testing needs to be the standard. I also hope that I've convinced you that standardized test methods are really critical and needed. We need to continue to work towards developing those. And they also need to consider how translatable they are to the real world conditions and applied settings under which these technologies would be used. And also just to mention that the HEPA units under these test conditions were more effective than the far UV sources for the tests that I've showed today. So a few additional considerations to leave you with that Aileen sort of alluded to or hit on previously, but I'll reiterate here is that all of the antimicrobial performance claims are required by law under FIPR to have substantiating data. So things that I like to look at, especially knowing that there's no true performance standard for these pesticidal devices, are things like, was the testing conducted by an independent lab? Were there replicates? Is the testing reported to be reproducible? How were the tests conducted? What microorganism was used? What size chamber was the testing conducted in? How was the efficacy calculated? So again, was that calculated based on time match controls or comparing, say, a final aerosol concentration to a time equals 0 concentration, which wouldn't be taking into account that background amount of natural decay of the microorganism. Again, how translatable are those test conditions to real world or applied settings? And how might differences between the lab and the field impact technology performance? And some other things to consider, obviously, are the associated costs and any sort of logistical considerations that would be associated with deploying various air cleaning and treatment technologies to get to understanding the holistic impact of the strategies that you're choosing to select and deploy. And then something that I haven't had time to talk about today, as it's not the focus of my work, but is the area of a lot of focus for emerging and important research related to using air cleaning and treatment technologies, is the safety part of all of this. So what about things like byproduct formation or a radiation exposure by these from these particular types of technologies. So for more on that, I'd like to point you back to the excellent webinar that was given last month by Dr. Jose Luis Jimenez on the health benefits versus disbenefits from air cleaners. And with that, I'd like to wrap up by stating that this is the work of a large EPA and broader community project team, and I'm grateful for all the input and support from them. And with that, I'll pass it back to Vito, and I believe Aileen and I are ready to answer any questions.
Thank you so much to both of you. You have really given us just a picture of the complexity on both the technological side and on the legal side, essentially, of dealing with some of these devices. And we have had a lot of questions that we'll try to get through, but it's in the order more or less of which they were received, which means that the bulk of the earlier questions will be for Aileen, and then and then we'll move on to Catherine's presentations question. But some of them will be probably for both. So let's start with the relationship really between the EPA regulations of these devices and what the FDA does. I think, Aileen, you mentioned that earlier. And so to what extent are FIFRA devices also regulated by the FDA? And is the terminology, for example, the same? So if we see this word sanitize on dishwashers or clothes washers, does it still mean the same as EPA means with sanitizing?
So I'm not sure about FDA's definitions. However, some dishwashers, some laundry detergents, laundry sanitizers are actually EPA registered. There are a few liquid sanitizers, and there is actually a washing machine itself that's a registered pesticide. And there are no products that currently fall into this category, but there is possibility that a product could be dual regulated by FDA and EPA. So I guess if you believe your product may fall into that type of category, please feel free to reach out with some questions, and we can direct you in the right direction.
Great. And there, you've probably seen the resources and links available for webinar participants. So one big overarching question that has come up again in public discussion is why are pre-market reviews not conducted for devices?
So when the regs for EPA and pesticides were written, devices were just excluded. Right now, we are working on a federal register notice to provide some clarification. But if there were to be a change that would involve registering devices, that would need to be rulemaking, and we would need to go through the rulemaking procedure.
Okay. And then you mentioned also that a company should keep their data demonstrating efficacy to them. Can EPA require a company to provide the data to the agency to demonstrate that their claims are not false or misleading?
So right now, there's not a formal mechanism to review efficacy data for devices. However, there have been times where we have requested efficacy data to make a determination on a product. Sometimes how the product works can be seen in the efficacy data. And that's where we might request something like that to make a determination. But as of right now, there is no mechanism to review device efficacy data.
Okay.
Sorry, Aileen, can I just interject here to ask one clarifying stuff? So, but based on, if there were a formal complaint filed about a device and a device making a false, or a manufacturer making a false or misleading claim about a device, under those circumstances, does EPA review the efficacy data?
Sometimes it would really depend on what the question is, what the product is, and what claims they're making. And again, sometimes it's not, we would request data. I don't know if we would require it.
Okay, thanks.
Then we have a couple of questions on allergens, and so could you repeat the requirements for air treatment devices in regard to allergens, and are there minimum removal standards under FIFRA that apply to allergens?
Yeah, so allergens is a broad term, and under an allergen, it includes both living and non-living organisms. So the best example is mold and mildew. Those are considered alive microorganisms. Pesticides are used to kill, repel, mitigate, or destroy them. So allergens, kind of as a broad term, would be considered pesticidal because it does include this mold and mildew. However, if the allergen claim is qualified to remove mold and mildew, so the claim would read allergens with a qualifier, and the qualifier would lead to pet dander, dust, and pollen, those are not considered living organisms, and the product would not, that claim that's qualified would not be considered pesticidal. So it does seem like we could be splitting hairs, but that's not what we're trying to do. We want to make sure that all products that are making pesticidal claims, including these broad allergen claims, which do include living organisms, are included as part of a pesticide.
Thank you. Then I summarize a number of questions essentially asking, what about this type of technology? What about UV shining on a filter? What about, how would you classify photocatalytic titanium dioxide and so on? So questions about a spot evaluation of these type of devices. What can we say to that? How can people understand or find out the classification of their devices?
So if you have a specific device that you would like a determination on, you can submit a PREA M009. This is a fee-for-service request where you make a FIFRA determination and we review the product and make a determination if you're a pesticide or a device or another one of the an exempt, if you fall for any of the other exemptions. Kind of that second part is currently we view photocatalytic apparatus. So if there's a photocatalyst that works with a UV light, that photocatalyst is considered a pesticide requiring registration. And there's going to be a clarification that hopefully will include that as well. But if you have any specific questions, you can email the mailbox that I posted on my slides of OPP_FIFRA_jurisdictional_issues@epa.gov, and I can look at your specific product and answer any questions.
Thank you. And then there's a question about handling all the information about a device on the label, and the question is whether this can be referenced in user manual, for example.
So yes, if there is a label and it references a user manual, that user manual would generally be considered labeling as well if it says refer to the user manual. And there additional directions on how to use the product, that would probably fall into that category. Additionally, if you have a website on your product, the web link that it goes to, so for example, if it goes to a website for productx.com and you have that on your label, everything on that website would also be considered labeling. And that also cannot have any false or misleading claims.
Thank you. Then we have a number of questions about whether parts of devices, specifically the UV light bulbs, need to be treated as devices. They need to be registered. They need to go through the process. If it's something that, for example, is imported and then the final customer assembles on their own, how are those treated?
So another non-answer is really it depends. So it depends what type of claims are made with the product when it's in the channels of trade. So for example, if there is a UV light and just the light bulb that is being sold or distributed and it doesn't make any pesticidal claims, that product may not be regulated under the EPA. However, if the UV light bulb is making claims such as a qualified germ claim on the UV light, that would be maybe considered a pesticidal device. It would also depend if the part that's being sold or distributed is integral to the function of the device.
Okay, so it's a complex thing.
It's
Okay, depends on case by case. Okay.
Yes, but more information can be found on our website, and I will find the link and put it in the chat.
There's a question, probably more to understand exactly this mechanism, but could you give an example, not necessarily a specific one, but of a device that has been registered as a pesticide? What kind of mechanisms of actions could be used as an example?
So I'm not sure I understand the question. So a device.
So is there an example of a device that has been registered as a pesticide?
So pesticides, if the product is a pure device, are not registered. However, if it's sold with a substance, so for example, a bug zapper with a lure, that would be that would need to be registered because it's sold with a substance.
Okay. And this is a question probably for both, but there are other efforts. I think, Catherine, you've talked a little about this briefly, but there are other efforts to come up with essentially with standards to test these devices. And the question is that you are aware of, how is EPA coordinating with some of these other ASTM or ASHRAE or other standards of this sort?
So maybe I could start, and then Catherine, maybe you would mind jumping in. So under PREA 5, there is a set aside for generating device guidelines. I believe it's $500,000 was set aside for developing these guidelines over the course of PREA 5. And it may seem like a lot of money, but it does go quickly. A lot of the equipment is incredibly expensive. So with that, we do have a set aside from Congress to work on these guidelines. And then we have been working with Catherine in her office. So I'll kick it over to her. Thank you.
Yeah, sure. So like Aileen said, we're excited to help work with OPP to help develop test methods for technologies that are currently considered devices that may end up being registered as parts of clarification down the road come out. But I'd also add that I and a number of my colleagues are involved in standards test method development. So I'm actively engaged in a number of standard test method development efforts through ASHRAE, and I know other, like I said, colleagues are associated with other groups through ANC and other types of standards development bodies. So EPA is engaged in these processes, and I'd also like to mention that our Office of Pesticide Programs is actively working to develop a testing framework and set of potential recommendations for air treatment products, so things that would be registered by EPA as pesticides, but would be making claims against microorganisms in the air. And the hope would be that some of the guidelines and some of the core information from that kind of testing, even though it's targeted towards pesticide products that would be registered, could be translatable to pesticide devices as well. So we are certainly aware of and involved in these various efforts.
Thank you. And this is another point that has come up a lot in the questions, and so let's try to make it as clear as possible. These terms, sanitation, sterilization, low-level disinfections, and so on, are they defined somewhere in EPA regulations? At the same time, is there specific methods, such as specific microorganisms, that need to be used to make these claims?
So I can take the first part of that. Is there, we do have guidelines for registered products that do involve the definitions of disinfectant, sanitize, sterilize, and those types of methods. However, because devices aren't registered and there are no specific guidelines they have to abide by, and they're in the same marketplace as registered pesticides, to maintain an even playing field, we do have the same definitions across pesticides and devices.
I mean, those are part of the OCSPP 810
Yes.
guidelines. So
yes,
I wonder if we can find and put a link to those in the chat. But there's, some, if you Google OCSPP 810 guidelines, the various definitions associated with performance will come up as part of those documents. And the one that's particular to or specific to air is the OCSPP 810-2500 guidelines for air sanitizers. And for those air sanitizer products, the current guidelines specify a 99.9% reduction within a 5-minute contact time. So that's the specific air-based claim for air products that are out there. So anything hypothetically less than that, a lower log reduction or a longer contact time from a pesticide product standpoint, I believe would be considered an air treatment. And I like using the word treatment. Treatment is part of the title of this webinar. We use treatment because it doesn't have that regulatory connotation in terms of a specific definition associated with performance benchmarks or particular microorganisms. So if you talk about air treatment devices, know that you're safe in calling it air treatment, and there's not a FIPR related connotation to that. It's a broad, all-encompassing way to talk about performance.
Thank you for these clarifications. And Catherine, towards the end, you mentioned the potential issues that is still an area of research on secondary pollutants that can be generated. And the question is, are these addressed anywhere in the regulations right now? And the follow-up question is, if so, how do they address the potential spectrum or the individual sensitivity to such pollutants?
Yeah, so I can start to address this, and this is all, me speaking in my personal capacity and not being obviously within the regulatory office. But from a device standpoint, claims about device performance in terms of their efficacy and safety cannot be false and misleading. So there are some very broad there's some very broad coverage of safety under FIFRA, but generally speaking, a lot of these devices are regulated from a safety standpoint, particularly UV, more closely by FDA that regulates, and FDA is more in the regulatory lane of the radiation emitting devices, and then also the Consumer Safety Protection Bureau has a role here, but I'll pass it over to Aileen to correct me and provide the wiser regulatory voice here.
Yeah, so false or misleading claims is kind of a broad section of claims. And there are a few that are kind of stand out, and we do have some resources. And like I said earlier, generally if a claim is false and misleading for a registered pesticide, it would likely be false and misleading for a device. So I would recommend people look at our pesticide registration manual. There is a whole chapter on claims and what is false or misleading. While it's not a direct one-to-one with registered products and disinfectants, it'll give you an idea of what would be considered false or misleading.
And just one more thing to add on to that, Eileen, you mentioned that the fact that the FRN from a few decades ago doesn't encompass or cover all of the more complicated technology that we're seeing now. So just to say that, as there's a growing recognition of byproducts and other types of safety concerns that are associated with various emerging or even, technologies that have been used for decades, but we have better ways to characterize the types of things that they're emitting into indoor spaces. There's certainly, a gap between when the regulations were written and what we know now.
Thank you. And we mentioned a moment ago the issue of time. So are there specific requirements to factor in time so that what might be considered soon enough or fast enough in the context of a claim under FIFRA?
So for registered products, we have an upward cap of 10 minutes. However, this is not a requirement for devices. But what we would encourage and would require is that there is a contact time in the directions for use. So for example, if it takes 30 minutes for the air treatment process to fully run, on the label we would like to see that, and the data that is developed to support those types of directions for use should match the directions on the label and with the product.
One, complicating factor that I'd add in here is that those contact times and the performance targets are, again, as we've talked about today, that they're a function of the test method and the testing environment. And so, we don't all live in test chambers. So when we talk about a contact time in a 1,000 cubic meter test chamber, the performance is going to be very different in something like a classroom or an auditorium. So having that specified contact time is, more increasingly important as we start to hone in on standardized test methods, but and with the lack of standardized test methods that are out there, it's really important to understand the context under which those performance numbers are generated associated with a specific contact time.
Thank you. And actually talking about that, the differences between test conditions and real indoor environments, with regards to the test chamber experiments that you showed, Catherine, is there any concerns about the fact that there are recirculation fans in there, whereas real environments may not be as well mixed?
Absolutely. Real spaces are likely, not going to be as well mixed as our test chamber. And that we know that the efficacy of certain technologies like upper room germicidal or upper room UV are going to be a function of that mixing. And so understanding the mixing in the environment is really important to be able to translate the results from a well-mixed lab setting to the real world. And so certainly it's something to consider and something to keep in mind.
Great. And two questions still on the tests, but were you able to study the effect of humidity on efficacy And or also were you able to measure ozone production during the tests?
So we have rudimentary ways to measure ozone in our lab space. We have measured elevated ozone concentrations with some of the pesticide air treatment devices that we have tested, and not with others. But I'll say that there are labs like those that exist within NIST that are much better equipped to do these kinds of measurements, as well as academic labs that are focused on these types of chemistry measurements. And so they're much better suited to address things like the production of ozone. But I'll just say that we have seen some elevated concentrations of ozone for some technologies and not with others. For the devices that we for the results that I showed in the devices that we tested today, we didn't see any sort of appreciable elevated ozone concentrations with our, like I said, pretty rudimentary instrumentation. And then the other part of that question was humidity. We have done some tests to look at changing relative humidity from like 30% to 50% RH and looking at our bioaerosol stability, and depending on how we're aerosolizing, what the media is, and we see increased stability at lower humidity levels or potentially higher humidity levels. So we've looked at the impact of changing relative humidity on just the bioaerosol stability, but we haven't yet been able to dive into how that those ranges of relative humidity interplay with the potential efficacy and the impacts of the effectiveness of the technologies. But that would be something that we'd hope to address in future work.
Another question about the test conditions. Many devices, certainly some HEPA devices, they come with different speed settings for the fans, and so but with higher being louder. So under what conditions were these devices tested?
These particular devices were tested on high. I will say that the devices we tested also have a UV component, that a photocatalytic component that can be turned on and off, and we have looked at the impact of turning that component on and off in a different set of results, but didn't talk about that here today.
And can you say something about the choice of MS2, given that it's much more resistance to UV than many other airborne pathogens?
Yeah, certainly. So we, in our efforts, have been looking at all different kinds of air cleaning and treatment technologies, like I mentioned, not just UV. So things like actual chemical air treatment products that would be registered as true pesticides, photocatalytic devices, ionization devices, all different kinds of technologies. And so it was important to us to choose a potential surrogate microorganism that we knew was going to be relatively conservative across these different mitigation or intervention strategies. So MS2 is something that has been widely used in bioaerosol research. It is safe to work with. It's easy to work with, relatively speaking, from a microorganism method standpoint. And so it was a logical choice for us to use for this, because when we're publishing results about effectiveness and efficacy of these various technologies, we want to be confident that if something is going to work against MS2, it would be working against those target respiratory pathogens. And so MS2 is a good choice, again, knowing that it's relatively resistant to a range of different technology types compared to the enveloped some enveloped viruses like SARS-CoV-2 or other potential types of respiratory pathogens. Another thing to consider, is something like M. tuberculosis is going to be more resistant than an enveloped virus to various things like UV and activation. And so we feel strongly about using a surrogate microorganism that's going to be broadly relevant to a range of different infectious aerosols. So again, MS2 is a good choice there.
Thank you. There's a question about the independent labs that can do challenge tests and whether EPA plays any role in accrediting these labs. Is there a list of accredited labs somewhere?
There's not, that I'm aware of, a list of EPA endorsed labs. There are certain, good laboratory practices that are, important from a registration testing standpoint. Aileen, do you have any more information on the types of labs that are used for registration-based testing?
For registration testing, the labs would be ones that conform to the good laboratory practices. But for devices, since the data is not reviewed or submitted for registration, they don't need to comply with that requirement like the registered products do.
Okay, thank you. I think at this point we have reached 2:30. I really would like again to thank the speakers for their time and their insights shared with us, and thank you everyone for participating in our webinar. You may want to remember the recording will be posted on our website. Look for it between 2 and 4 weeks from now. And thank you again. And this concludes our webinar.